Substitution permutation networks use dense layers of key mixing and structural confusion to hide data. To the outside observer, they appear as an impenetrable mathematical maze. Differential cryptanalysis bypasses this complexity by utilizing a chosen plaintext attack. Instead of passively intercepting data, the attacker actively selects specific inputs to feed into the cipher. We do not analyze these inputs in isolation. We structure the data into pairs, creating tuples that consist of two plaintexts and their two resulting ciphertexts. The core requirement is that the attacker selects plaintext sharing a fixed, precisely engineered XOR difference, denoted mathematically as X prime. We then observe how the network processes the difference between these two texts. Tracing this differential, rather than the raw data itself, exposes the internal mechanics of the encryption. We are not attempting to brute force millions of possible keys. We are locating a mathematical fault line in the cipher's architecture and applying targeted pressure. The exploit begins at the input phase of the cipher round, where the data is combined with the secret subkey using an XOR logic operation. When we evaluate our pair of inputs entering the round, we can calculate their input difference using this specific formula. Because XOR logic is both associative and commutative, we are mathematically permitted to rearrange the variables, grouping the two unknown key values together. This reveals the fundamental vulnerability of the operation. Any value XORed against itself cancels out to 0. The equation condenses. The input difference entering this round is proven to rely strictly on the output difference of the previous round. The secret subkey bits for this round have entirely vanished from the mathematical reality of our input difference. Because the key chemically drops out of the difference equation, we gain a transparent window through the mixing layers. We can calculate how bit differences cascade through the system with zero knowledge of the actual key. While the key cancels out during the mixing stage, the data must still pass through the S-box layer. This is the cipher's nonlinear component, engineered to disrupt predictable patterns. In a theoretically perfect scenario, an S-box would take an input difference and map it with absolute uniformity across all possible output differences. This table shows the empirical data. When we feed an input difference of 1011 into the S-box, it maps to a severely limited cluster of specific outputs. The distribution is highly skewed. Cryptanalysis calculate these outcomes for every possible input-output combination, standardizing the brute force mapping into a master grid known as a difference distribution table. This table displays the full distribution map for a standard S-box. If we isolate row B, which represents our previous hexadecimal input of 1011, the lack of uniformity is obvious. We see an abundance of zeros, indicating outputs that never occur. Conversely, we see highly concentrated clusters, like the 8 in column 2 and the 6 in column C. These specific clusters are our targets. We denote the specific count of pairs matching these exact input-output states as n sub d. By dividing that value by the total number of possible pairs, we calculate a propagation ratio. This allows us to treat the S-box bias as a measurable conditional probability. Even though the S-boxes effectively hide the raw data, their inherent mathematical biases provide a predictable, mapped vector that we can exploit.
Identifying a single biased S-box is useful, but the attacker must navigate the entire multi-round network. This schematic shows the full architecture. Notice how the outputs from one round physically permute into the inputs of the next. We can chain our calculated probabilities together to form a differential trail, a continuous sequence of highly probable transitions spanning multiple rounds. We begin the trail in round 1, targeting the active S-box 2. Based on our distribution table, this specific transition occurs with a propagation ratio of 1/2. Following the permutation layer down to the second round, the difference activates S-box 3. This secondary transition holds a distinct propagation ratio of 3/8. Moving into round 3, the difference spreads, activating two separate S-boxes simultaneously. To find the probability of the difference surviving this entire path, we apply a mathematical assumption. We treat the rounds as independent events. We multiply the propagation ratios of all the active differentials together. The math yields the exact probability for this full sequence. By chaining these localized biases, we have built a predictable mathematical bridge. We can feed a specific input difference into the cipher and accurately predict its state at the doorstep of the final round.
With the theoretical probability model established, the next phase is writing the software to execute the attack. Algorithm 4.3 dictates how we use the theoretical trail to statistically filter out the correct final subkey. The code begins with a major loop, iterating over every intercepted tuple of plaintexts and ciphertexts. The algorithm's immediate goal is to identify a right pair, a specific tuple whose data successfully navigated our calculated differential trail. It filters the data by examining the inactive S-boxes. If the tuple followed the trail perfectly, the inactive boxes must produce identical outputs, resulting in an XOR of exactly 0. Any tuple that fails this check is categorized as random noise. Discarding them immediately prevents the algorithm from wasting massive amounts of computational power. The core execution loop then takes the surviving right pairs and decrypts their final round, testing every single possible candidate subkey. Each time a candidate key produces an intermediate XOR value that matches our predicted trail, the software increments a counter for that specific key. As the data is processed, the candidate key with the highest frequency count mathematically rises above the noise, statistically proving itself to be the true final round subkey. We bypassed the encryption key using XOR math, exploited the S-boxes to build a predictive trail, and filtered for right pairs to extract the final subkey. However, this exploit is entirely dependent on statistical dominance, which requires a strict volume of data to succeed. The precise volume required is defined by this equation. T represents the total number of chosen plaintext tuples the attacker must intercept. Epsilon inverse is the reciprocal of the probability bias we calculated when building our differential trail. For the specific 3-round network in our example, the mathematics dictate that the attacker must capture between 50 and 100 tuples to guarantee a break. Theoretical mathematical security cannot survive if the underlying architecture contains measurable biases. When an attacker acquires a sufficient volume of targeted data, the encryption will systematically collapse.